All right, good morning, everybody. Today and Wednesday are very big, powerful days in terms of conclusions and all the stuff we're going to do to describe motion and all the little details and parts. So I'm going to go over some of the basic rules and develop some of the ideas of the calculus that we can do to vectors that we may or may not be aware of. And one of the most important ones is product rule for dot product and cross product. It's not obvious what's exactly happening. So let's consider the following. Let's consider vector u, keep it simple, is, let's say this is x1 of t, excuse me, y1 of t, z1 of t, and vector v, let's call x2 of t, y2 of t, z2 of t. Make sure I got my notation correct. I just have two random vectors, and what I want to do is do the dot product and talk about the derivative of the dot product. So the first thing we're going to do is u dot v, which of course would simply be, I'll write it in this form, x1, not vector, sorry. Will be x1, x2 plus y1, y2 plus z1, z2. Okay, great. Okay, understanding these are all functions. So this answer is a function of t. I would like to differentiate then the result, meaning I want to differentiate all of this. Now these are all functions of t, so what am I going to have to use in order to do this derivative? Differentiating a bunch of products? Probably product rule would be a good thing. I heard something the other day. I was having a conversation and one of the physics professors was complaining because they had a 196 class where they had a lot of students who didn't know what the product rule was. I find that a little hard to believe that you could be in a physics 196 and not know what the product rule is, because you learned that really on like day 5 of Calc 1, and then you've used it, oh what, a million times. But they were students who didn't even know there was such a thing. At least that's what they claimed. That kind of scares me, because of all the things you ever do in calculus, this is one of the easier things because it's just a simple algorithm. So product rule, I'd have first times the derivative of the second plus the second times the derivative of the first. And I'm going to go all the way through. And y1 times dy2 dt. I know the notation looks kind of ugly, but it's just easier to write it like that. dy1 dt. And then z1 dz2 dt plus z2 dz1 dt. Wow, that's busy. You know, what if I pull apart? What if I pull apart some of these? Can I pull apart some of these derivatives in such a way that it's really easy to read? For example, what if I put, I'm going to regroup these. So what if I put this one, and this one together in one grouping, and put this one, and this one together in a second grouping? Might be easier to see where this is going. So the first one would be x1 dx2 dt plus y1 dy2 dt plus z1 dz2 dt plus, and then the second one would be x2 dx1 dt plus y2 dy1 dt plus z2 dz1 dt. Okay, right, because addition is commutative. Do you see a couple of dot products right up there? Wouldn't this one here be x1, y1, z1 dotted with dx2 dt, dy2 dt, dz2 dt? Does everybody see that? Clearly that's a dot product. And then the second one would be x2, y2, z2 dotted with dx1 dt, dy1 dt, dz1 dt. which means this is u dotted with dv dt plus v dotted with du dt. Can we all see that? Is this a good thing? This is a great thing. Because the derivative of a dot product just simply follows the product rule. So I wanted to differentiate this dot product. Took a lot of work, didn't it? But the derivative of the dot product is first times the derivative of the second plus second times the derivative of the first, just like the product rule for functions. By the way, that's a great thing. I don't have to reinvent it, okay? And it's an automatic thing. So that's a very, very handy tool, that the derivative of a dot product just simply follows the product rule, verbatim. But they're still, right, still vectors in the dot product. So I'm going to look at one of the more important results for that. Let's suppose for a moment, okay, let's start with vector v. Let's suppose vector v is of constant magnitude. Now, there's a couple of ways something can be of constant magnitude. I can have a vector of constants, in which case its magnitude would be a number, not a function, in other words. Or I could simply have a unit vector, in which case its magnitude would be what? 1. So there's multiple ways I can have a vector of constant magnitude. So let's just sort of generically say this. So that means that the magnitude of vector v, let's just say, is constant c. Okay? I have some vector, its magnitude is a constant. It's either a unit vector or it's a vector of constants. By the way, it can also be something like a motion where I have sines and cosines. Some of you guys saw that, right? When you're finding magnitudes of things with lots of sines and cosines, you get lots of cos squared plus sine squareds under roots. And oh, okay. There's many, many ways I can have a vector of constant magnitude. You know, the helix examples, things like that. So let's start by supposing I have a vector of constant magnitude. Then what I'd like to do, then what I want to do is differentiate. I want to do d dt of v dot v. The vector dotted with itself. Well, let's see. According to the product rule, this should be first times the derivative of the second, that's what we just derived, plus the second times the derivative of the first, because it's v dot v. And of course, this would be the same as just saying it's 2 times v dotted with its derivative. Okay, that's really exciting. The derivative, by the way, this is true for any vector, that the derivative of a vector dotted with itself would be this. Okay? But isn't a vector dotted with itself equal to the magnitude of the vector squared? We've already looked at that one. We know, because what's magnitude squared? Well, that's, I'm squaring the square root. So it'd be the v1 squared plus v2 squared plus v3 squared. Okay. Huh. So shouldn't this whole quantity equal the derivative of the magnitude squared? By the way, this is always true. This is true for every vector that exists, that the derivative of a vector dotted with itself, you're differentiating the magnitude squared, would give me this. Okay, so what's the big deal? What did I start by assuming? I started by assuming the magnitude was constant. Oh, is that important? Kind of. What does that mean this is equal to? 0, because I'm differentiating a constant. Okay. Is this important? Yeah. Is the derivative of a vector dotted with itself equal to 0? No. No. Of the infinitely many vectors, you can count them on one hand how often this will be true. No, 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 no. The derivative of a vector dotted with itself is not 0 unless the vector's of constant magnitude. Remember, magnitude is always going to be a function of t. So the derivative of that is probably something really complicated, messy, and gnarly. But if the magnitude is constant, then the derivative of it is going to be 0. Okay, so why is that important? So now that comes down to this right here. In fact, forget the 2 for a moment. I'm saying twice v dotted with its derivative is 0. So that means that v dotted with its derivative is 0. Okay? Is that a big deal? If I'm starting with a vector of constant magnitude, we have just proved that the vector dotted with its derivative is 0. The only way a dot product is 0 is if the 2 vectors are orthogonal. Ooh. Yeah, that's like astronomical conclusion. This is one of the most important conclusions that exists in all of physics. That if you have a vector of constant magnitude, it is orthogonal to its derivative. Vectors are not orthogonal to their derivatives in general. No, that's a 1 out of infinity proposition. No, vectors are not orthogonal to their derivatives. Vectors of constant magnitude are orthogonal to their derivatives. That is huge. That is really huge. That means the derivative of a unit vector will always be orthogonal to the unit vector because the unit vector was of constant magnitude. So this turns out to be a very, very important result and a very, very useful result. Okay? So with this, we're going to define something. We're going to define something called the unit tangent vector. Okay? So I'm moving along space, and I hit the banana peel in space. So I know I'm going to slide. Right? When you're think you're on an oval track and you're driving your car and you hit a wet spot and you hydroplane. You're going to go on a line. But what direction are you going to move? You already know. What direction are you going to go in? What do we say? A direction that is tangent to the curve. Agreed? So, I'm moving along in space. I hit, right here is the banana peel. That's the direction I know I'm going to slide. Something tangent to the curve at that point. So the unit tangent vector is a vector that describes your motion at that point, but we want a unit vector. Well, what vector do we already know is in the direction that you're going to slide? The velocity vector. So the unit tangent vector is the unit vector in the direction of the velocity. That's exactly what it is. So we define, so we started with r of t, then we know its derivative is defined to be the velocity vector. That tells me the direction I'm going, but the velocity vector is not a unit vector in general. So I want to make it into a unit vector. So what we do is we define the unit tangent to be 1 over the magnitude of the velocity vector times the velocity vector. Okay? Last week I showed you, this is a very important identity, that the magnitude of the velocity vector was also the arc length parameter. It's also ds dt. Those are the same things. Because remember, if I asked you what is the magnitude of the velocity vector, well, you say it's the, dx dt squared plus dy dt squared plus dz dt squared under the square root. But that's also exactly what the arc length is. That quantity under the square root that you integrate. So we showed last week that these are identical things, and you use whichever one is convenient at the moment you're using it. Because they are always exactly the same thing. And the reason I say you use whichever one's convenient, if I wanted to take a derivative, taking the derivative of the magnitude of a vector as a general statement can be kind of a complicated statement. So it might be easier to use this representation because it's already in a derivative form. If I'm doing the actual calculation and I want magnitude, it's probably easier to do this form because I already know this is a square root of something. These are interchangeable, which means I can also write this way. 1 over ds dt times v of t. Okay, this is a function. Okay, it's ds dt is probably not constant. Now, remember, most of the time when you're dealing with things like this, you're going to evaluate them at particular values of t. So now you have vectors of constants. But you have to do the derivatives and things first. So this is what we define to be the unit tangent. So let's do a really simple example. The unit tangent in general is just not very hard to find. So let's suppose I give an r of t. Let's say r of t is t squared, 2t, 3t squared. All right, give it. Sort of interesting. So dr dt, which is v of t, would be the vector 2t, t, 60. What is the magnitude of v of t? Well, it'll be this squared, plus this squared, plus this squared. Let's undo the root. Okay, you with me on that? So what do I got under the root here? I've got, looks like, 40t squared plus 4. Now, whenever you're making a unit vector, you're going to have roots involved, and you're going to have roots involved in a denominator. It can get really icky really quickly. So a good idea often is, if I can simplify this, you want to do so because it's always better to work with smaller quantities if you can. Is there any perfect squares in here? 4, so can I factor out a root 4? Yeah, in which case this would be 2, and then that would be 10t squared plus 1. In the long run, that will probably be easier to work with, okay? And when it comes to roots, you always want the smallest roots possible because it can get really big and ugly really fast. So now I want to define my unit tangent vector. It's going to be 1 over that quantity times the vector 2t, 2, 6t. So when I multiply that in, clearly I can cancel some 2's. So I'm going to have t over the root, 1 over the root, and then looks like 3t over the root. Okay, not pretty, but that's what it is. Now, I'm pretty sure I did everything right. Pretty sure I did everything right. Is there a simple way to check that I, assuming that we didn't mess up the derivative, assuming that from here to here we're okay, that's probably the easiest part of the problem. That's supposed to be a unit vector. If I didn't mess it up, it's a unit vector. Is there a simple check to see if something's a unit vector?
Cross product?
No, it's simpler than that. It's actually not complicated. What do you think?
Take the magnitude of it, and if magnitude is 1.
Okay, now how do you do the magnitude?
Just
Square plus square plus square has to equal 1. But those are so big and ugly, then just look at the numerators because all my denominators are the same. As a simple rule, like never deviate from this rule. Always leave your denominators the same. But what if I can reduce one? I always like to use the example of 12. I have denominators of 12. So I have 3 12ths, 4 12ths, and 6 12ths. So if I reduce them all, I'll have halves and thirds and fourths, and now I have denominators of different numbers. Then when I do the cross products and the dot products and things, I'm going to make mistakes left and right because I'm dealing with multiple fractions of different denominators. Never do that. No, if you have a quotient, to the best of your ability, keep all of your denominators the same. It will make your life so much better, so much easier. Okay, let me square the numerators. T squared plus 1 plus 9t squared, that's 10t squared plus 1. I'm done, that's my check. I just squared my numerators and added them up, and they added up to 10t squared plus 1, which is what the denominator would be if I squared it. Therefore, everybody see that, how easy that was? If your denominators are the same, just square your numerators and add them up. And then you can tell really quickly. Because is it possible that I reduced badly? Is it possible that just something went wrong? Yeah, it's always possible. So this is the unit tangent. As a general rule, the unit tangent is not difficult to find. The derivative of the unit tangent, more often than not, is. Would you be excited to find the derivative of that? No, yeah, you've got quotient rules and product rules and chain rules. You got all the rules at one time. The derivative of the unit tangent, as a general rule, is not a happy thing, but you're going to have to do it because I need the derivative of this for the second half of whatever problem we're answering. Yikes. So let's take the derivative of this, and I'm going to show you why you need that. Okay? We don't know what we're going to do with it yet, but it's probably important. So let's find it, and we write it this way, dt. Yikes. I got to take a bunch of derivatives. Well, I'm kind of lazy. If I get the derivative of the first term right, do you think the third term's going to be really complicated? Or will it just be 3 times that? So let's get the first term right, and then the third term is kind of an easy one. So I need to differentiate each of these. So let's start by differentiating. Now, hopefully you remember this from Calc 1. Anytime you have a quotient, you can use quotient rule. Should you always use quotient rule? No. If your denominator is something raised to a power, do not use quotient rule. It will take you exactly 3 times as long to get the right answer. That's to get the right answer. Usually it only takes half as long if you want the wrong answer, right? But it takes about 3 times as long because you have to do so much simplifying. If your denominator is something raised to a power, always write it as a product. There is no exception to that. Absolutely every problem that exists, I looked at all of them last night just to make sure, every problem that exists, if your denominator is something raised to a power, will be a fraction of the steps if you write it as a product. And we all know that product rule is usually easier to execute than quotient rule because it's sums of products, where quotient rule is differences of quotients, and I can get things wrong. So I'm going to rewrite this as what? T times 10t squared plus 1 to the negative 1/2 power. Now if I do product rule, it will be much easier. And I'm far less likely to make an error. Okay, so first times derivative of the second, but now I got to use my chain rule. So that'd be negative 1/2 10t squared plus 1 to what power?
Negative 1/2. Or, sorry, negative 3/2.
Negative 3/2 times the derivative of the inside, which is 20t, plus the second times the derivative of the first. So plus 10t squared plus 1 to the negative 1/2 times what? Good. Now this is a common problem in Calc 1. Not a problem you loved in Calc 1, but a common problem. I need to write my answer in its most condensed form, and probably a quotient would make the most sense. I don't want a negative exponent in my final answer, so the simplest way to do that is don't make this into 2 quotients. No, factor out the greatest common factor. So how do you choose the GCF when you have the same quantity multiple times? You pick the one with the what? Biggest or smallest exponent?
Smallest.
Smallest. So what's the smallest exponent?
Negative 3/2.
Negative 3/2. And the best part is they only differ by 1, which means when I factor it out, the other one's going to have an exponent of 1. So I factor this out, and what's left? Well, I took all of it. I have t times negative 1/2 times 20t. What's that? That's negative 10t squared? Yes? No? Maybe? Now, on the other side, these differ by 1, so this leaves me an entire factor of 10t squared plus 1. Okay. That looks kind of good, doesn't it? Are these going to cancel? Yeah. What does that leave me with then? 1 over 10t squared plus 1 to the 3/2 power. Oh, well, that wasn't terrible. I mean, it wasn't great, but it wasn't terrible. Okay. Well, I already know what my third position is going to be. So now let's find the second position. So now I need to differentiate just this, so there's no product rule on that one. That's actually easy. I'm just differentiating that piece. And when I differentiate that piece, when you differentiated that piece, isn't that what this is right here? The derivative of this without the t. So when I differentiate that one, it was negative 1/2 this to the negative 3/2 times 20t. So what's that going to be? There's nothing to factor out. That's just going to be then negative 10t over 10t squared plus 1 to the 3/2. Yeah, I'm being really lazy. It's right there. That's the derivative of that piece. And then finally, what's the third piece? Third piece should be 3 times what the first piece was. So what's going to go here? Let me erase that, sorry. 3 over 10t squared plus 1 to the 3 halves. Now, I just differentiated the unit vector. Is this a unit vector? That's a good question. Is the derivative of a unit vector generally? Turns out, rarely. If I have sines and cosines, I might get lucky, because it's still sines and cosines. But in general, the derivative of a unit vector is not another unit vector, unfortunately. And an easy check would be, do the same thing with your numerators. If I square this guy, I get 1. Square this guy, I'm going to get 100t squared plus 9, so that's 10 plus 100t squared. Is that what I get if I square the bottom? No, not even close. No, this is not a unit vector. Never make the assumption that the derivative of a unit vector is automatically going to be 1. You might get lucky, but it's probably not the case. But here's what is important. I want to do something here. If I said, what is t dotted with dt? I know it's kind of a distance. I want to take that vector and dot it with that vector. Well, the easiest way to do that is do the numerators. Because they all have the same denominator, they all have the same denominator. When I multiply denominators, won't I just get 10t squared plus 1 quantity squared? Because those are to the 1/2 and those are to the 3/2. So when I multiply denominators, that's actually nice, that I don't get any roots. But let's look at the numerators first. If I do the numerators, what do I get? I get t plus negative 10t times 1 is negative 10t. Then I get 3 times, where am I? 3 times 3, am I doing this right? Hold on a second. T times 1, oh, okay, plus 9t, here we go. And then my denominator we just said was 10t squared plus 1, quantity squared. Okay. And what does this equal? 0. 0? Yeah, it's supposed to be 0, isn't it? I just dotted a unit vector with its derivative. We just did a proof a few minutes ago that said that's always got to be 0 because they're orthogonal. I'm doing a quick check to make sure I didn't mess up the problem, but they are orthogonal, aren't they? That's a good thing. Because that now gives us impetus to define the second unit vector that we need to know about. We defined the unit tangent. Now we're going to define what's called the unit normal vector. Now, where have we used the term normal vector before? Give me a simple example where we've used normal vector before. Yeah, a plane is defined by the normal direction. By the way, when you found your normal vectors, right, you did a cross product to find a normal vector, was that vector a unit vector? In fact, if you did an infinite number of problems, you're probably never going to have one that's a unit vector. No. The normal vector you found in the plane is not a unit vector. It doesn't need to be one. No, it's because I just need any vector that's on that line would be good. But I want a vector that's actually a unit vector to get this. Well, how do I find it? You make this into a unit vector. So the unit normal vector is the unit vector in the direction of dt. So I find my unit tangent. That's usually a fairly simple thing. But then I take its derivative, which usually isn't a very simple thing. Now I have the direction, but that's not a unit vector. I still need to make that into a unit vector. Yikes. That's not a trivial concept in general. So we just did all the work. That is the correct vector, and then we dotted it with the unit tangent just to make sure. But now I need to make this into a unit vector. Okay? And by the way, that's not a complicated process. It really isn't. So I now need the magnitude of this guy. Okay, so it's this squared. Actually, since I'm going to have the same denominator 3 times, let's just square the numerators first. So I'd have 1 plus 100t squared plus 9 all over 10t squared plus 1 cubed under the square root. Which would be 100t squared plus 10 under the square root over 10t squared plus 1. I'm going to write it to the 3/2 because it was under a square root. Can I make that quantity prettier? I can factor out a square root of 10, but is that, I don't know if that's a good idea or a bad idea. Maybe it's a good idea? Let's see what happens. This is kind of a personal choice. Because I can't factor out any perfect squares, I can certainly factor out a root 10. And the reason I might want to do that is then this would look like 10t squared plus 1 under the root, which is kind of all over the place in this problem. So how do I get the unit normal? It's 1 over the magnitude, this guy right here, times dt dt. So if I take the reciprocal of this guy, all of these guys are going to cancel, aren't they? Does everyone see that? All of your 10t squared plus 1 to the 3/2 terms, every one of them is going to cancel. That's a good thing. And what does that leave me with? That leaves me with 1 over the numerator. And then the next one would be negative 10t over. And then the last one would be 3 over. Because when I multiply by the reciprocal of this, again, all of those denominators would cancel. My numerators are staying intact, and that's what I would get. Now, this is the part I like. When I look at this and I look at this, now it's really easy to see that that dot product's going to be 0, isn't it? Look at your numerators. So this is the unit tangent, that's the unit normal. Now, as a general rule of thumb, when we're talking about motion, I don't always want the unit tangent and the unit normal as functions. Because I'm going to say, okay, you're moving around, and right at this point, which direction is your unit tangent, which direction is your unit normal? Which means you're going to usually be evaluating both of these. Like, so I might say, okay, now I want you to evaluate these at t equal, just give me a number, t equal 1, t equal 2, t equal 5. So what will happen is that these vectors end up being vectors of constants at some point because you've evaluated them. See, when you're driving on your trip, I'll say, well, how fast were you going on your trip? No, how fast were you going at that moment in time? That's more of a comment. Yeah. How fast were you going at that moment in time when you got pulled over for the speeding ticket? You know, not what was your average speed of the trip. So this is kind of messy, but this is what it is. So now, visual aids. Okay. I am moving through space. There are always two vectors. As it turns out, there's a third vector, but it's not that important. We're going to talk about it next day. There's a third vector, believe it or not, that goes like this. We're going to introduce next class, but briefly. I'm moving through space. There's always going to be two vectors, two unit vectors that are orthogonal. So as I'm moving through space, let's say this one is my tangent vector. There's always going to be a unit normal vector. Now remember what I said about motion. If it makes it easy, just think about moving on the floor. So I'm really moving two-dimensionally in 3D. Right? I'm just going to move along the floor. It might be easier to conceptualize. All motion is linear, it's circular, or somewhere in between. Usually somewhere in between. So if I'm talking about motion, I know I'm probably going to need that later, but I'm moving around in space. So at this point right here, clearly there's the tangent direction. And then that would be the normal direction. But what about when I'm here? That's the tangent direction. Would the normal be this way, or would it be up? It'd have to be up because when I'm moving, the two combined, in fact, my acceleration, this is the whole point of next day's lecture, my acceleration can be defined as a linear combination of capital T and capital N. all motion that exists is actually a linear combination of those two, or I should say the acceleration vectors, which describe your motion. So if I'm moving on a line, then I have 0 in the normal direction, don't I? If you're moving on a line, then you have 0 normal. If I'm moving on a circle, we showed this last day, remember I moved on a circle and we saw the acceleration always pointed directly towards the center. The acceleration points exactly in the direction of the unit normal vector, if you're on a circle. Oh, so if I'm on a circle, then all of my acceleration's in the direction of the unit normal and 0 in the direction of the unit tangent. If I'm on a line, it's all in the direction of the unit tangent, 0 in terms of the normal, and everything else is some combination. So most motion is a linear combination. It's how much is in this direction, this is a unit vector, how much is in this direction. The more in this direction, the straighter your motion. The more in this direction, the more curved your motion. Does that make some sense? Oh, okay. Now notice this had to go the other way because I'm turning to the left. I'm not turning to the right. Oh, so if the amount that I go in this direction is going to influence how much I turn there. If more of it's in this direction, so let's say my motion is 10 of these and 1 of these, and I'm pretty straight. Okay? I'm not actually going to be curving all that much. So all motion eventually is going to be a linear combination of the tangent and normal vectors. Now the coefficients, that's the tricky part. That's next day's class. How do we determine how much in each direction? That's kind of a big deal. So now the next major concept, I've got this turn. Okay. How many here you park your car on a street, let's say, particularly a residential area? Anybody? So you got to leave this morning and you're going the other way. So you got to turn around. So how do you turn around? Do you go like this, or do you go, most of us do that, right? But do you have a car that can turn around in the street? Anybody have that car? So what do we say? What kind of language do we say about that car? It has a really...
Turn radius?
It has a really turn radius? Usually an adjective. Really small turn radius, tight turning radius. Some adjective that says, I can turn really tight. And we use words like turning radius, which is actually a correct term. But then you have some big, you have a big boat that you drive and you have to do this like 3 or 4 times because it doesn't turn very much. Okay? We'd say it has a lousy turning radius. What it means is it has a really large turning radius. And in terms of a car, we don't like really large turning radius. It makes it difficult to turn around, makes it difficult to parallel park. But what is that referring to? It's referring to exactly the right thing. As I'm moving around in space, at every point, now I'm going to give you a 2-dimensional picture, but we're still moving in 3D. I can draw tangent lines easily. All of us can conceptualize tangent lines easily. But I want you to picture tangent circles. At every point there's a tangent circle. So this tangent circle would be really small. This one here, probably about there. How about here? Huge, because it's barely turning. At every point on a curve, there is a tangent circle. At every point on the curve. And the tangent circle is on the inside, it's not on the outside. Because it'd be like saying, well, right at this point, if I drew a circle, that would be the circle I draw. But that was a really tight one, because when I'm turning my car, so imagine when you're turning your car. When you're turning your car on the road, do you at some point have to release the wheel? Because what would happen if you're turning your car on the road and you never release the wheel? What is going to happen eventually? You will carve out a perfect circle. That's not physics, that's just simple common sense. If I turn my car, I'm on the street, I just turn it a certain amount and I just keep driving, I will eventually describe a circle. We consider with a car a small circle to be better than a big circle, but we would carve out a perfect circle. That's why at every point on here, there is a circle that if I just kept my steering wheel, so think of this as a windy road if it helps. At every point, there's a tangent circle. The unit normal vector points to the center of that circle. That's an absolute. Always. The tangent is easy, right? The unit tangent. So I'm going in this direction. So here, let's say, I know my unit tangent is going that way. I know my unit normal is going that way. It's not how long the vector is because it's a unit vector. You made it a unit vector. But the tighter the circle, the smaller the circle, the more curve the road would have. Do you agree? Very curvy, very small circle. Fairly straight, huge circle. How big is the circle if I'm on a line?
0. Doesn't exist.
No, it exists, but really big, right? How big? Infinite. Yeah, it'd be infinite radius. Which is, by the way, not useful at all, but since every point has a tangent circle, okay, so make it easier on yourself. Your curve is gradual, huge circle, and you're straightening out, huger circle, eventually you're going straight, infinite circle. But you're going straight, so that's almost irrelevant, because I said if you're going straight, there's no multiplier on that other guy. But there's always still a circle. So I would like a numerical value to describe how curvy the road is. But not necessarily as a general function. I'd say, how curvy is it here? How curvy is it here? How curvy is it here? So in other words, how curvy is it at this value of t? Because I'd really like to give you numbers, because do you agree that it's not going to be a constant? The only way it's a constant is if you're on a line or on a circle. Those are the only times. And what we're calculating is called curvature. Curvature is a measure of how curvy you are. So the more curvy, the smaller the circle. We'd say there's tremendous curve here. The straighter, the more, right? Less curvature because it's more straight. Big circle, little curvature. Small circle, big curvature. In fact, what we're going to see, it's not really important at this moment, but a really nice result is the actual numerical value of curvature is the reciprocal of the radius, as it turns out. And that kind of makes common sense. The smaller the radius, the bigger the curvature. The bigger the radius, the smaller the curvature. If it's ending up being straight, we'd say there isn't any curvature, which is why the radius technically would be approaching infinity. Oh, okay, that makes some sense there, doesn't it? So, there it is. So we need to define curvature. So the definition is a little bit tricky. So I'm going to give you two-dimensional pictures, but curvature, when we describe curvature, we're usually working in 3D. You can have two-dimensional curvature. There's nothing wrong with that. I can have all my motion on the XY plane, and I still have curvature. But because we're describing motion in 3 space, we're really never going to do two-dimensional curvature. It's always going to be 3. Now, I could be moving around the floor. I am in 3D, but there's no z component to my motion. That's okay. There's nothing wrong with that. But we don't want to limit ourselves. So I have a curve. Okay, here's my r of t. And what I want you to think of is, at every point, think of a unit tangent vector. Okay? I have little unit tangent vectors at every point. Think of curvature as the rate of change of the direction of my unit tangents. Would you say my unit tangents aren't changing direction tremendously rapidly through this portion? It's fairly straight, so there's not a whole lot of direction change. But there's a lot more direction change here. The rate of change of the direction determines the curvature, but how do I do that? I do that by considering r not as a function of t, but as a function of the arc length. Oh, so for every change in arc length. So think of arc length as for every unit of arc length, how much am I changing? Not for every second, how much am I changing, but every unit of arc length. So we define curvature, strangely enough, curvature is defined, and by the way, we use a k for curvature. This is one of the things that I think is funny when people want to use ij, k for vectors. The most important constant in a vector is k. K is the curvature constant. And k is part of every vector, as you're going to see in a moment. So if you're using k as a vector and k as a curvature, which you would in every vector that exists, it can be a little confusing. Just like, as you're going to find later, in linear algebra particularly, vectors always have imaginary numbers in them. So every vector actually has i's in almost every position. So if you're using ijk, that gets a little confusing. I've never actually seen anybody pull that one off correctly. So since I and k are used in almost every vector that exists as constants, you probably don't want to use them also to represent your vector. What I'm saying is every vector that exists has an I as a number and an I as a vector, a k as a number, a k as a vector, yikes. And in engineering, what's the same as I? J. They use j for square root of -1. I don't know why. I just find that to be really confusing. But when you see j used, you know, oh, it's an engineering problem. It's the same thing. So that's why the ambiguity and the confusion and the overlap of the same symbols to mean completely different things in the same, you avoid it. We define this to be the rate of change. This is a really weird thing. Of the unit tangent with respect to the arc length, not with respect to time. So look at my picture. I'm going to take every 1 unit of arc length. So don't even think about time. I want to take every unit of arc length and draw the tangent vector. So literally every 1 unit, draw a new tangent vector. How fast are those guys changing? That's why it's a magnitude. How fast is the rate of change of the direction of the unit tangent with respect to 1 unit of arc? It's a weird sounding thing. You're never going to find a vector of s. But I start with that. So now we need to use a calculus concept of chain rule to remind ourselves. And you've done this before. If I said, we'll keep it simple. If y was actually equal to y of x, then we say dy dx is the derivative. Nobody ever writes y of x, do they? We just write y. But what if ultimately x was actually a function of t? Then can I ask the question dy dt? You'd say, yeah, it's the derivative of y with respect to x times the derivative with x with respect to t. This is called the chain rule. We often use the chain rule with function notation. If I had f of g of x, then we say, what? F prime of g of x times g prime of x. That's exactly the same thing. First one would be my dy dx, and the second one. The chain rule is sort of like keep differentiating until you get to the innermost variable, if you remember. From a notation standpoint, you go, okay, yeah, I see. But this is just chain rule. It's no big deal. We know this from Calc 1. This literally is at the very beginning of Calc 1. When you have a composition of functions, you got to do a chain rule. So what I'm saying is, I know s is actually a function of t. Right? That's the arc length parameter. But s is a function of t. So t of s, not exactly because s is a function of t. It's really t of s of t, isn't it? So I want you to, this is vectors. So we're going to use the chain rule on this. You'll like this. It's not that complicated. I want dt. Well, wouldn't that mean this has got to be dt ds times what? ds dt, which is not a vector, that's a scalar value function. Oh, so what is, again, so this is not complicated, but I got to get it right. So therefore, what is the derivative of the unit tangent with respect to the arc length would simply be 1 over ds dt. I'll put it in front, times this. Did we just do this to find the unit normal vector? Yeah, so curvature and unit normal kind of go hand in hand in their calculations, as we're going to see in a moment. If I do one, I usually can do double duty, you know, because I'm doing the same kind of stuff. So going back to this statement right here, that means that this is equal to 1 over ds dt times the magnitude of dt dt. But isn't ds dt the same as the magnitude of velocity? So could I therefore write this as, actually, sorry, I'm going to put this up high. No, this is hard to read if I write it too low. Could I write, therefore, could I do that instead if I chose? Yeah. Oh, magnitude of velocity is almost always an easy thing. Magnitude of the derivative of the unit tangent, not so much. That can be a really gnarly thing. So I'm going to show you an alternate route. I called them backdoor methods. Every calculation we do has a direct calculation and an indirect. Indirect meaning I'm going to show you another way to get to the same result by using basically properties of things. So the curvature, which is defined to be this, you're never actually going to find this. You're going to do this. Okay? If I'm given the speed, then it's 1 over the speed times this magnitude, which is the same as just writing it this way. I can put these in a quotient because these are both magnitudes. Curvature could only be 0 if I'm moving on a line. Okay? That's a simple rule. So that's curvature. So let's go back to the previous problem that we just did all this work on, if you will. I believe my original vector, I'll rewrite some of it. R of t was, it was t squared. Read it back to me. It was t squared. 2t
squared.
What was the last one?
3t squared.
3t squared. Okay, good. That was our thing. And t of t, I think it was t over the root. Is that right? And then 1 over the root. And then I think it was 3t over the root. Okay. I think we had all of this stuff. Correct?
Yeah.
So now, I would like to know what the curvature is. Well, in the last problem, we found that the magnitude of dt, I believe we found that to be, again, I'm going off the top of my head. That was our denominator, correct?
Yeah.
What was, our numerator was square root of, is that the one that had 100 in it?
100t squared plus.
I don't actually remember these things very well. I do make them up on the spot. Does that look right?
I think that one was 1.
Was this the magnitude of dt?
Oh, the mag.
And then we multiplied by the reciprocal to get the unit normal.
Yes.
But we needed this to get the unit normal. Okay, so I want to go back to this. In this problem, we calculated this also, and I believe this was 2 times the root, correct? Fortunately, we didn't do it that long ago. I'm actually remembering. Was that the magnitude of velocity? That one wasn't hard. So now, if I asked you for this particular vector valued function, at any point in space, can you tell me the curvature? Yeah, and by the way, usually you'd be telling me the curvature at a particular value of t, but it doesn't really matter because you got to do all of this in terms of t. A common mistake people make is they try to evaluate and then do all their derivatives. That doesn't work. You got to do all your derivatives and then evaluate. So for this particular problem, if I asked what's the curvature, well, you'd say it's this quantity divided by this quantity. Okay, so what does that end up being? That's 100t squared plus 10 over, if I'm dividing by this quantity, then that means on the bottom I'm going to have 2 and then 10t squared plus 1 quantity squared. Agreed? Does that reduce? Yes, because I can factor a root 10 out of the top and I can cancel some stuff. It does reduce, it's not a pretty thing. So it's far more likely you're going to say, okay, what is the curvature at t equal, and then I'm going to give you a number. So I would probably rather evaluate these guys at t equal a number, and then take the quotient and reduce my root, because my answer would be just a scalar, not a function. But this is kind of nasty. Curvature in general is not a simple, easy thing to find in general, because the fact that this guy here is usually kind of messy, because you have square roots of functions in the denominator. The exception would be if you have sines and cosines. So our example of a helix and things, curvature is absolutely trivial in those kind of situations, because your derivatives are so nice, your magnitudes are so easy. When you're doing sines and cosines, all calculations are easy. But you're not always doing sines and cosines. I gave you a function. Would you agree that this is not terribly complicated? I mean, there's no exponentials, no logs, no trig, no inverse trig. It's just t and t squared. That's pretty low level. Yet, see how busy this got, how gnarly it got really quickly? That's more the norm. So, given any vector valued function, you can tell me the unit tangent, usually pretty easily. Unit normal, probably a bit more work. There's almost no way around that. And now I've defined the curvature, which can be kind of icky. So I'm going to show you an alternate way of finding the curvature. Now, if you go to Canvas, I do have a set of pre-printed notes on curvature that you can go back and look at. It gives you the whole derivation and does all the shortcut forms. We're going to be piggybacking on all of the results today to get all of our results next day, because we need all the same stuff. But some of the tricky things involve things like magnitudes of cross products and stuff from a different point of view. So I'm going to walk you through. Sometimes I'll bring up the lecture notes on the board. This one is not that complicated, but it does involve some stuff you may not be thinking about. Now, we know this. We know this is 1 over the magnitude of v times v. Okay? I'm going to leave that the of t. That's implied. I generally write of t in everything, just so we don't lose. But understand everything is a function of t. So if you wanted to write capital T, you're not doing anything wrong. When you're doing calculus and you write y, does any of you write y of x? No, it's implied because it's a function of x. It's totally okay to write a capital T because there's only one variable, little t, anywhere in the problem. But a lot of times we'll write the little t because when I take my derivatives, I kind of need to get the right notation. So everything's of t. Then is it correct to say that v equals magnitude of v times t? Would this be true? Everybody okay with that statement? And then I want to write it this way. ds dt times t. This is a scalar valued function multiplied by a vector. I use the term scalar valued function all the time, and everybody, of course, oh yeah, no one ever admits, I have no idea what that means. That's the only thing you've ever worked with in your entire life. A scalar is a number. A function is not a number, and you cannot equate functions with scalars. You would always get the wrong answer. No. But if I evaluate my function, I generally get a scalar. So why do we use the term? Because functions don't always produce scalars when evaluated. If I have a function of more than one variable and I evaluated one of the variables, I still have a function of every other variable. It's never a scalar. That's not a scalar valued function. A scalar valued function is if I have a function of one variable and I now evaluate it, I now have a scalar. We're going to start with functions of multiple variables next week. All right, f of x and y. But if I only evaluated one of the variables, I will never get a scalar back again. Does everybody understand that? Oh, okay. So we have to make sure we understand. So this is either a scalar or it's a function of t, which would be a scalar upon evaluating. I like that. I can work with that. That's never going to be complicated. So when I say scalar valued function, it means it might be a scalar, it might not, but ultimately it's going to be a scalar upon evaluation. And I need my vectors to be vectors of scalars at some point. Right? So when I say, well, how fast were you going at that, at that point in time? You don't give me a function answer, you give me a number. Okay. So we do want numbers at some point. So if I write it in this form, and the reason I would write it in this form, because now taking a derivative will be so much easier. It'll be much easier for me to take a derivative if it looks like this. Everybody with me on that? It's hard to take a derivative of something that doesn't look like a derivative. So what do we know about A? Isn't that dv dt? So wouldn't that be the derivative of this? Stare at that for a moment. Function vector of t. So I still have to do product rule. And the derivative of a vector stays a vector. The derivative of the scalar value function stays a scalar value function. So I don't want to lose the vector. I'm going to have vectorish stuff. I'm going to have a dt somewhere in this. All right. Okay? This is the definition of the unit tangent, so I just rewrote it like this. I rewrote it like this. We know this is true. So I'm going to take a really strange route to get acceleration is equal to this. Okay? So when I do this, what do I get? First times the derivative of the second plus the second times the derivative of the first. Now, to make my life easier, I'm going to put the vector second because, generally speaking, okay, if I said to you, I want 3 times vector v, would we write vector v times 3? No. If you do that in physics, even if you had everything right, you'd get 100% wrong. No, you can't write a coefficient after a vector. It has no meaning. There's no analogy there. No, coefficients have to precede the vector. They can't come after the fact. I have people put them after the fact all the time. No, it's not commutativity there. Scalar times scalar is commutative. No, you don't put the scalar after the fact. So therefore, this has to go in front of the vector. Now, product rule, right? First times derivative of second, second times derivative of first. So what's derivative of first? That would be d squared s dt squared. Don't really know what that is yet, but I'm going to put it in front of the vector so that it reads like a vector. So I have something times this vector plus something times this vector. Okay? Now, I want to walk away from that for a moment. Okay? That, by the way, we're going to come back to this tomorrow. Turns out this is huge. In terms of big results, this is how we're going to get stuff. Because don't I already know this guy right here is a multiple of the normal vector? Don't I know that? We showed that earlier. Oh, then I can manipulate this to show you that the acceleration is something times the normal plus something times the unit tangent. That's kind of the next thing. But that's not what I'm doing today. So now that I have that, I want to do something totally wacky. I now want to do V cross A. But I want to use this version of V, and I want to use this version of A. You with me? Because I know this is an alternate way of writing the velocity vector. Nobody would ever start with the unit tangent and then come up with the velocity. It's the other way around. But we know this is the relationship between them. And we just did another alternate way. So I want to do V cross A, and we're going to do it by doing it this way. So that would be ds dt t crossed with ds dt 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 plus d squared s dt squared t. Now again, that's of t. Now, let us do this. If I do a vector crossed with itself, just remember what you get. If you cross a vector with itself, what are you always going to get?
Vector squared. 0.
not 0.
0, 0, 0.
A vector crossed with itself is the 0 vector. BC minus BC is 0. AC minus AC is 0. AB minus AB is 0. In case you forgot that. That's something you actually should have known from physics. A vector crossed with itself. So a vector crossed with any multiple of itself is the 0 vector. Not the number 0, but the 0 vector. Is that an important thing? Yeah, I'm going to be crossing T with T in a moment. Oh, okay. Yeah, that is actually a very important thing. A vector dotted with itself is the square of its magnitude. A vector crossed with itself is the 0 vector. Here's where it's confusing. If two orthogonal vectors are dotted, I get the 0 vector. But if two orthogonal vectors are crossed, then I get a vector that is orthogonal to the plane that exists, right? Same direction, good for dot product, bad for cross product. Orthogonal, bad for dot product, good for cross product. Okay? Yeah. Lest we forget, these are things that we know. These are absolute facts. Let's do this. Cross product is distributive. It's not commutative, but it is distributive. So the first one's going to be ds dt, quantity squared, t cross dt dt. So far, so good? Then what's the next one going to be? Plus ds dt times d squared s dt squared times t cross t. Okay. I'm just going to write it in that form. Make sure I didn't lose anything here. So did I get all that right? Make sure I got all that right. So okay, good. Now, this is the 0 vector. This is a vector. I'm adding it to the 0 vector. I'm not adding it to the number 0, but everything on the right here is now 0, 0, 0, so there's nothing to add to this result. You with me on that? There's nothing to add here. Okay? So then the last piece of the puzzle, make sure I get all this right. I don't know what this is, but I do know something. V cross A is a vector. What is the magnitude of a cross product? Do you remember? What's the magnitude of the cross product? Magnitude, magnitude. Something missing. And times the sine of the angle. Magnitude of the dot product was magnitude, magnitude, cosine. Right? Magnitude of the cross product we showed is magnitude of the first, magnitude of the second, sine of the angle between them. I would like to find the magnitude of V cross A. Well, let's see. If magnitude of that term is obviously 0, so it would be the magnitude of this. Agreed? I'll just write big terms like this. Oops, this is ds dt, quantity squared, t cross dt dt. Okay. Well, isn't ds dt the same as magnitude of velocity? Don't we know those are interchangeable? So you know what I'm going to do at this point? I'm going to write that as magnitude of velocity squared. Why not? Might be easier to look at. Magnitude, magnitude, sine of theta. This is lovely. This is wonderful. This should make you excited. What is the magnitude of the unit tangent?
1.
Aren't these vectors orthogonal? Didn't we prove it? So therefore, what's the sine of theta?
0 or 1.
1. Sine of 90 degrees. Oh, is that a good thing? It's a great thing. That only leaves this. This is the only thing left. Nice. So what have I got? At this point in the game, we have V cross A magnitude is this times this. Okay? Now I'm going to go back to, I don't need this anymore. What is curvature in terms of magnitude? Didn't we just show that curvature was this? Do you agree? That's what curvature is? Then doesn't that mean that the magnitude of dt is what? I hate racing stuff, but doesn't that mean it's k times the magnitude of v? I just replaced this with magnitude of v curvature. Your new best friend. You're never going to run into a problem where that's difficult. Ever. That's what I call the backdoor. Curvature is the magnitude of that cross product divided by the cube of the magnitude of velocity, or the speed cubed. How do I know that? Because I just went back to here and replaced one with the other. What we did earlier was we found everything directly, and that was kind of gnarly, wasn't it? Everybody agree? That it was kind of gnarly. Now let's go back and look at the problem from a different point of view, the one that we already did. And I'm going to start with the original vector, and I'm going to show you how nice this is. Now, the question people always ask is, well, then why don't I just always use that one? Because if you have something that's not difficult, finding it directly will be a fraction of the time. No, that'll take 3, 4, 5 times as long if you can calculate it directly. But if calculating it directly is really long and involved, like what we did, then that's probably faster. And even if it's not faster, it might not be faster, but it's probably a lot easier. And I don't care about how long it takes me. I don't want it to be complicated. Right? When you have denominators that are square roots and now you've got to take derivatives, it can get really messy really fast. So let's write down the obvious. So the r of t that we used earlier was t squared, 2t, 3t squared. The velocity then is 2t, t, 6t, and the acceleration is what? 206. We didn't need the acceleration before. All right. Now, next thing. V cross A. 12 minus 0. 12t minus 12t. 0 minus 4. That didn't seem very complicated. Again, 12 minus 0, 12t minus 12t, 0 minus 4. I don't think we have any errors here. I think that's correct. What is the magnitude, therefore, of V cross A? So 12 squared plus negative 4 squared under the root. What would that be? Calc 3 students. I shouldn't be challenged by adding two small numbers together, I hope. What is this? 4 root 10? Okay, good answer. I want curvature. We've just figured out our numerator, haven't we? Okay? We've already done this, but in case we forgot, it's just this squared plus this squared plus this squared under the square root, which we said before was what? 2 this? Is that correct? Okay. I now want curvature, and because I did not give you a specific value, we're going to state curvature as a function, which is kind of the messiest way you could possibly do it. But that's what we're going to do. Usually at this point of the game, I'd say, I want the curvature at, and I'd give you t equal a number. Once you've found acceleration, you're never going to take the derivative of acceleration, are you? So you can, at this point of the game, you could always evaluate things. So if I said find it at this particular value of 2, or of t, you would go ahead and plug in your numbers now, because you're done taking derivatives. But you don't do it prematurely, because then you're taking derivatives of scalars. But we answered the question earlier as a function, so let's go ahead and do that. So in this problem then, curvature is 4 root 10 over 2 times 10 squared plus 1 under the root quantity cubed. Yikes. Well, let's see. That would be 4 root 10 over 8, 10t squared plus 1 to the 3/2, which would be root 10 over 2, 10t squared plus 1 to the 3/2. That would be my most reduced form, wouldn't it? There's nothing else I can combine or cancel. And remember, you'd probably be evaluating this. Now, what form, when we did this, and we definitely did it the long way, we didn't make it easy on ourselves, what was the final form we wrote? I believe it was the square root of 100t squared plus 10 over 10t squared plus 1 squared. Was it not?
It was 2 at the front of it.
Oh, and there was a, thank you, there was a 2 there. Was that the form we had? But on the top, we could have factored out the root 10 times 10t squared plus 1 to the 1/2, canceled with one of those, and got that answer. That's actually a more complete answer. This route was long. I gave you a very, very simple function. There were no complicated functions. I only have one term in each. I don't have sums and quotients in each position, right? There's no transcendental functions. That's about as friendly as you can get, yet that problem is still a lot of work. So therefore, the backdoor, doing it this way, will still give me the same answer. Now, there are times I still have to find the ugly stuff, depending on what I'm looking for. But if the question only was asking you for curvature, way simpler to do it that way. In fact, what part of this process, when I went this way, what part was complicated? None. There was no part of this that was actually really even challenging, especially from a calculus standpoint. The only derivatives you took were this direction. You didn't differentiate the magnitudes or quotients. That's kind of nice. You said, well, then why don't I always do it this way? Let's look at a helix. I love helixes because I can picture them. All right, let me take a real simple one. Let's say R of t is, how about 4 cos t, 4 sine t, I don't know, 2t. Let's say that's our helix. We did problems like this recently. I want to do everything in this problem. And I don't care about a particular value of t yet. Again, most of the time you're going to do this at a particular value, but we also want to be able to do it in general. So we're going to do it the formal way, right? dt, dt, and that kind of stuff. So what is the velocity vector?
-4 sine t, 4 cos t.
Cos t, 2. I now need the magnitude of the velocity vector, which would be 16t squared plus 16, sine squared, 16 cos squared plus 4. And what would this be? Well, That'll be 16, correct? So this is altogether what? Root 20? Which I'm going to write as 2 root 5. You don't have to do that. But if you don't do that, you're working with larger numbers in an unreduced root for the rest of the problem. Clearly, I'm going to get cancellation if I use that, so I'd rather use that. Remember, when working with roots, if you can reduce a root, always reduce it, because it probably is going to show up in a quotient and things may cancel. Things probably cancel. All right, so let's continue this problem here. So my unit tangent vector is 1 over 2 root 5 times negative 4 sine t, 4 cos t, 2, and that would then be what? Negative 2 over root 5 sine t, 2 over root 5 cos t, 1 over root 5. Now before I continue on, I want to do a quick check to make sure that's a unit vector. You say, well, why would I need to check it? You might not believe this. I mean, this class and linear algebra are both classes we do a lot of things making unit vectors. A very high percentage of the time we get to this point in the problem, it's not a unit vector. Does anybody know what is the universal error that people make at this point? They don't multiply through by the reciprocal of the magnitude. They multiply through by the magnitude itself. Oh, how often does that happen? I'd say at least a third of the time. If my magnitude particularly involved quotients, and by the way, sometimes your magnitude can involve quotients because the numbers you use might not be friendly. So I have a magnitude that is already a quotient. So looking at it as reciprocal, nothing's really registering in my brain. So if I multiplied by the wrong thing, I may not even recognize it. It is absurdly common that people will multiply by this rather than its reciprocal. So I'm going to do a quick check. When I square this, I'm going to get 4/5 sine squared plus 4/5 cos squared, which is 4/5, plus 1/5. Right? Always check, because the check is easy. But if this is not a unit vector and I'm going to use this for the rest of the problem, I'm going to get a wrong number somewhere. So I want to make sure I did this right. Now the next step of the problem, the next step is to find this derivative. So now I need dt, which in this case is going to be trivial because I'm just dealing with sines and cosines. We love helixes. So this will be what? Negative 2 over root 5 cos t, negative 2 over root 5 sine t, 0. So far, so good? Now I need this magnitude. So that will be 4/5 cos squared t plus 4/5 sine squared t plus 0, all under the root. And what will that be? So square root of 4/5, which is the same 2 over root 5 that we had before. What a shock. And sines and cosines, that's probably going to happen. So now, if I asked for the unit normal vector, we might as well take it as a freebie at this point. What am I going to do? I'm going to multiply this vector here by the reciprocal of this. And by the way, this is what I'm talking about. That's a quotient. It's already something that I'm not recognizing. If I multiply through by this, I will not have a unit vector anymore. If I multiply through by the reciprocal of this, I should. But that's the kind of error that people make all the time because they just don't realize it's an error. You always multiply by the reciprocal. So I'm going to multiply by root 5 over 2, and what's going to happen to these guys? They're going to cancel. And therefore, what will I get? Negative cos t, negative sine t, 0. There's my unit normal. I'm pretty sure I did it right. Is it a unit vector? Yeah, that's pretty easy. And is it orthogonal to the unit tangent? That's the other check. I'm going to get 2 over root 5 sine cos minus 2 over root 5 sine cos plus 0, and that is 0. Mini celebration. It's supposed to be 0. Where, if I'm going to make an error at this, if there was a mistake, it wasn't the unit vector, what would be the mistake? Sines and cosines, what's always the mistake? Plus and minus signs. Do you all agree? I'm differentiating sines and cosines. We mess up plus and minus signs. That's literally the only error anybody ever makes. But if I have a SIGN error, that dot product won't be 0. So if I do a dot product and I don't get the number 0, now I know exactly where to go check my plus and minuses. My dot product was 0, I'm feeling pretty good about right now. I know my unit normal is correct. There's only one other thing now to ask, and that is, what is the curvature? What is the curvature? It's the quotient of what? This value over this value. That's what we showed. So the curvature, which is the magnitude here over the magnitude there, and what does that give me? Is that 1/5? Does that look right? My curvature is 1/5. That's it. By the way, was this curvature complicated and difficult, or was it absolutely easy? Absolutely easy. In fact, I don't even have functions. Like, because of the sines and cosines, I don't even have functions. I just have numbers. Nice. So would it have mattered what value of t I gave you? No. Why is that? Because on the helix, all of your motion is circular. Your curvature is a constant. It's never going to change. It's like, oh yeah, that makes perfect sense. My curvature is never changing because I'm doing the exact same thing at all times. That should make sense. But usually in motion, right, my curvature is changing constantly. Okay. Most problems, curvature is not trivial. Now, let's do the problem the backdoor way, just to show what it looks like. Okay. So in the backdoor way, I need to do one more thing. I need the acceleration vector. Okay. I'm going to erase this because we don't need this for the backdoor. For the backdoor, the nice thing is all I need is the velocity vector and the acceleration vector. I don't need anything else. So there's the velocity vector. What's the acceleration vector? So the derivative of the velocity, so that should be -4 cos t, -4 sine t, 0. Now I want v cross a. So to do that, I'm going to put the v above it because it's easier for me if I can see it. So 0 minus, so that would be 8 sine t, -8 cos 0, and then 16 sine squared plus 16 cos squared. Agreed? Now, what are the nice things about magnitudes? Even if I mess up the signs on my cross product, will I still get the right magnitude? Yeah. This is the one time you can actually make a mistake and it still come out right. We don't want to do that, of course. So, what is the magnitude of v cross a? It's going to be 64 sine squared plus 64 cos squared plus 256 all under the root. Well, that's 64. So what do I actually have under the root? 320. Which would be root 64, root 5, so that's 8 root 5. Okay? So what is my curvature? It's magnitude of the cross product over the cube of the magnitude of velocity. So far, so good? Well, so this would be 8 times 5 root 5. Pretty sure that would just be, okay. It wasn't hard. Took a little longer, right? The direct way was a little bit faster. Any questions so far? Right?
What is the derivative of the tangent function represent again?
Oh, the derivative, okay, let's back up a little bit. Remember, any unit vector is going to be orthogonal to its derivative. We proved that. And by the way, what if I took a vector of scalars? Then the derivative of that vector would be the zero vector, wouldn't it? But didn't we prove the zero vector is automatically orthogonal to all of the vectors? So we haven't violated any rules. So if I have a vector v, and vector v is a unit vector, whether it's sines and cosines, whether we just made it a unit vector by dividing every entry by its magnitude, however we did it, it's a unit vector. It's orthogonal to its derivative. So now that I have the unit tangent, its derivative tells me the direction of the unit normal. It doesn't give me the unit normal, it gives me the direction of the unit normal. What does the velocity vector tell me? The direction of the unit tangent. Agreed? The velocity vector tells me the direction of the unit tangent, but I have to make it into a unit vector by finding the magnitude of the velocity. So the derivative of the unit tangent is probably not a unit vector, by the way, but the derivative of the unit tangent now tells me the direction of the normal vector. So I find its magnitude and I make it into a unit vector. That's how I find the unit normal in general. There's no shortcut for that one. Unfortunately, there's not a backdoor in that sense to find the unit normal. I will show you a trick, though. I will show you a trick that will allow you to find the unit normal when something's really, really gnarly and you don't want to do the formal way, but I need an answer. I'm going to show you a backdoor. It will work in the situation we're looking at. But the unit normal of all the calculations is probably the ickiest one. Because I took a vector, capital T, where every denominator had a square root in it, probably. And now I got to take its derivative, and then I got to take the magnitude of that derivative. Square roots everywhere. And we did that earlier, and we didn't even use a complicated R of T, and yet that whole process was pretty messy. Agreed? You're like, there's no way around it. But now I showed you this. You can do this every time. So one of the things I tell people, like in your notes, have both formulas side by side. And then you choose which one you want to use. Because it's always a context, situational thing. Depending on how the original problem was defined, it might not be that hard to do the direct method. Okay? It just might not be that difficult. But then again, it could be really nasty. Let me do a different problem that's not terribly difficult. Now let's see where this takes us. All right, let's suppose now, I'm going to give you a simpler R of T. R of T is 2T, 4, or actually 2T, 4T, 4. I'm going to throw a constant in. I don't want it to be. Okay, I took everything down a notch. Okay, the exponents and things like that. What's V of T? 240. What's the magnitude of V? 4 plus 16 under the root. So that would be 2 root 5. So what is now my unit tangent vector? Over root 5, 2 over root 5, 0. Now, we have an interesting problem here, don't we? What's the derivative of this vector?
0. Or the 0 vector.
It's the 0 vector. Ooh. So what do you suppose that means in terms of my motion in general? I made this kind of wacky and weird. In the XY plane, this is simply a line. What does that 4 tell me? Let me make it easier on you. X equals 2t, y equals 4t, so doesn't that mean that y equals 2x? Do you all agree with that? You know, that's the x-axis coming out at you, that's the y, that's the z. What does this look like in 3D? Hey, go up 4 units, and now you have the line y equal 2x. So what does this look like in 3D? It's a line parallel to the floor. It's the line y equal 2x, 4 units off the ground. So my tangent direction is, my tangent's constant, isn't it? I'm moving on a line. Remember, linear, circular. The helix is essentially circular motion. This is a line. So how much of this is going in the normal direction? None. That's why I'm not getting anything for the rest of it. This is not an exciting problem, by the way, just so you know. What's the curvature going to be? Curvature. What's the derivative of this vector? You said it's the 0 vector. What's the magnitude of the 0 vector?
0.
0, and that's the numerator of my curvature. Oh, I'm going to have 0 curvature. Why? Because I'm on a line. Radius is the infinite, not the curvature. You're never going to have infinite curvature, but you can, on a line, technically you'd have an infinite circle. It's infinitely large. It's not interesting. So I'm giving you an exception. I give you something that technically is linear motion. Because I made that third one a 4, that just messed everything up, didn't it? Okay? Now, what if I made this for t? It's still linear in the xy plane, but now what's it doing? It's rising, isn't it? It would still be a line, but now it's a line going this way. How do I know that? Because I could factor the t out of the problem, and it's just a multiple of a constant vector. Constant vectors are not interesting. They just aren't. There's not a whole lot going on. But I'm showing you that because that's the one that'll mess you up, because you're going, gee, nothing's working. No, everything's working. We're just done at the very beginning of the problem. That's why you think you did it wrong. No, it's linear motion. There isn't any curvature. That's why. There's no curvature. That's, like I said, that's a really boring problem. So that's not the one we're interested in. So if you've got nothing out of today more, can you give me a unit tangent? Can you give me a unit normal? Can you calculate a curvature? So let's see. The only thing I'm going to change now is, going back to the original problem, I'm going to show you some ways of looking at it based on the way a question's usually going to be asked. So again, we've already done everything. I'm not going to redo. So my r of t, t squared, 2t, 3t squared. Okay, that's a pretty generic problem as far as I'm concerned. So now what I want is, I actually want t of 2, n of 2, and k technically of 2. So now your final answers will not have any t's in them. Your final answers will have been evaluated at a particular number. So regardless of the route you take to get there, so my unit tangent, help me out, which one was this? This was, I know we had, let's see, this was 10t squared plus 1 in all of them, 10t squared plus 1. Give me a second. You tell me my numerators in a moment. 10t squared plus 1. Okay, what were my numerators? Unit tangent.
1, 1, and 3t.
1, 1?
No, t1 and 3t.
T1 and 3t. Everybody cool with that? Now I would say, and what is t of 2? 10 times 2 squared. What's that?
40.
40. So what are my denominators? Root 41s. And my numerator would be 2, 1, boy, this is the happiest, easiest check of all. 2 squared plus 1 squared plus x squared is 41. Whew, didn't mess it up. So now this is the answer. But the danger is I had to do this because I can't find the normal vector from here. I have to do it from here. Remember, I had to do derivatives of things. So you can evaluate anytime, but you have to take the derivatives of the things that are still functional. So what was our normal vector? What was our normal? What were our denominators in the normal? Were they these guys ultimately?
No, it was the root 100 t squared plus 10.
That was the numerator, wasn't it? Right. Help me out here. What was our normal vector? We did that early on.
That was 1 root 100 was t squared plus 10 negative.
Okay, so what were all the denominators?
Root 100 t squared plus 10.
Okay, all the denominators were this. Okay, just want to make sure. Okay, what were my numerators?
1, negative 10, and or 3.
Negative 10t.
Negative 10t. Okay, good. That was not going to work otherwise. Does that look correct, everybody? Okay.
10. Lower right. The right denominator.
Oh, thank you. Thank you. Okay, so now n of 2. So what do we got here? We've got 410, which is 10 times root 41, but I'm not going to factor out a root 10. There's really no logic in that. That's not a simplified answer. Root 410 doesn't have any factors that are perfect squares, so we would literally just leave it like that. It's not pretty, but that's, you know. So now we have 1, negative 23, and again, quick check, 1 squared plus 20 squared plus 3 squared is 410, and 2 minus 20 plus 18 is 0. What did I ensure? They're both univectors, their dot product was 0. These are the things I have to check because it's easy to drop a negative, it's easy to switch something, it's easy to leave something out. The one nice thing though, you notice I have the same denominator in each problem. I didn't have to work very hard to get that, but I definitely wanted to make sure, even if things canceled, that I left it the same. And now finally, in this problem, the curvature, because this, by the way, is the more useful version of an answer, because I want to know, I'm moving around space. I'm picking a particular point in space and saying, tell me about everything at that point. So you had to find things in general and then evaluate. The evaluation always comes last. So finally, what is the curvature? You can say k of 2, it helps. So what was the formula for the curvature? Actually, let's just do the formula. What was the formula we got the first time? It was, I think this was on top. Is that correct? No. That was on top. And we had 10t squared plus 1. The unsimplified version, wasn't it that?
And then there's a 10 or 2.
And then there's, I don't, for whatever reason, I just don't want to put that 2 there. Is that right? That was the first version we got. And then I showed later, hey, you could have actually factored and canceled. You don't need to because you're going to simplify your final version numerically anyway. So I'll leave that as is. Evaluate it at 2. So I have a root 410 on top. What do I have on the bottom? 2 times 41 squared. And what is that?
3,362.
So what, I'm sorry, what's the denominator?
3,362.
3,362. Now, there are no perfect squares in 410. So can I do anything with this? No, let's leave it alone. Is that a large number or is that a small number comparatively?
Pretty small.
That's really small. Yeah, if you look at a decimal, that's really small. So what is that telling us?
It's a small circle.
No,
It's not curved.
It's not curving very, yeah, it's fairly linear is what it's actually telling us. Remember, small curvature, big circle. One way of thinking, I said the radius of the circle is the reciprocal of the curvature. So if I said how big is the circle, I take the reciprocal of this value, which would be very, very large now, and then that would be the radius of our circle. Oh, okay. So when I'm on a road, now that I love using this because real life is nice. All right. You're driving down, okay, they've reworked Morena Boulevard a whole bunch in the last couple of years. Everybody know that? You know, Morena and Balboa, you know, they put all these extra lights and things. But you're cruising down Morena, going north. And you want to get off of Balboa. Everybody know what I'm talking about? And, or at least it used to be, there was a really sharp curve there. They kind of changed it a little bit. Anybody know what I'm talking about? Really sharp curve. You're coming down from Mount Soledad towards Torrey Pines Road. Anybody been on that road? Beautiful drive. Coming down Mount Soledad, you know what I'm talking about. Mount Soledad, and so there's a really sharp turn there. I can think of two places in San Diego County where the speed limit is 15 miles per hour, but only for a few feet. You're coming down, you see a sign that says 15 miles per hour. Pay attention to the sign. I have a friend who totaled 2 really, really expensive foreign cars. His dad was a doctor, and he destroyed 2 of them on the Mount Soledad turn. Totaled 2 cars because he ignored the 15. You're turning, it is so sharp that if you're going faster than 15, you're very likely to fly off the road and crash, which he did 2 times. The one, Morena to Balboa, they changed it, but that used to be one of them. The turn is so sharp. Where do they come up with these crazy speed limits? It's actually really simple. They're using the curvature of the road to determine the speed limit. There's actually a mathematical formula. All things being equal, weather being good, the road not being slick, the more curvy the road, the smaller. I'll give you an example. I have a family member who lives in North County, and there's a lot of windy roads to get to their house. And most of the time, people are going fairly fast, 40, 45, 50 miles an hour. And it feels like about every 30 seconds, you'll see a sign that says 25 or 30. You pay attention to that sign, because that means there's a really sharp bend in the road right then and there. And then it goes back to the normal thing. They're not doing that because they don't think you can drive. They're doing that because laws of physics say if you go much faster and you don't have great tires, you're probably going to leave the road. Literally, you're going to crash. I grew up in Santa Cruz County in a really small town, and I still remember there was this one street. It was very straight and then a sharp curve. And the house, they actually, in front of their house, they had a fence and it said Coffee. I think that was their last name. And everybody in the area knew that was they called it the coffee corner, but most people just referred to it as the coffin corner. And I grew up there, lived there for about 10 years. I'm aware of at least 30 times where they had to replace their entire fence because a car ran through it. At least 6 times that same car went through their front living room wall. Because the turn was so sharp and high school kids would be driving so fast, even though there was a speed limit there, they couldn't make the turn, they'd crash through the fence, and on more than one occasion, they didn't have a huge front yard. And I thought, what a horrible place to live. Can you imagine, watching the game and having the car come crashing through your living room? And that happened almost once a year, by the way, that a car literally went through their house in the living room. Because whoever built the road there, it was literally a right angle turn. But the speed limit was not bad going down the road. You just had to come to almost a complete stop to make the turn, which a lot of people didn't. The speed limits in those situations are simply designed so that you don't crash, and then you go as fast as you want afterwards. But curvature of the road, so if you've ever been on a windy mountain road, you know you probably got to slow down a little bit because the turns are more difficult to make. That makes sense, doesn't it? And that's, again, the speed limits. So when the speed limit is fairly high, then you know the road is probably fairly straight for a while. And then when you see the lower speed limit, okay, this is probably pretty windy coming up. It's actually a really simple thing to think about. Okay? So we've got these things, we've got them down. What we're going to do next day is now talk about how do I describe all motion in terms of its acceleration using all of these pieces. And it turns out there's multiple pieces of the puzzle. So we're going to figure out how to calculate the coefficient that goes in front of the unit tangent, how to calculate the coefficient that goes in front of the unit normal, and this ultimately describes all motion. All motion in 3 dimensions can be described the same way, and it's not really complicated. So we're going to work with functions that aren't much worse than the ones we did today, for the most part, just so we can navigate through the problem. Okay? Then that will mark the end of everything vector until the end of the course. Okay? It's going to mark the end of the material that will be on your first exam. So after class on Wednesday, sometime between Wednesday and the weekend, I'll be posting the practice test. And those who have been in my class, you know I put a thorough practice test and a key that covers everything we've covered, including quiz material and so on, that you want to practice certainly before we get to the exam. Our review will be a week from Wednesday, and then the exam, I believe, is the following Monday. The exam's like 2 weeks from now, even though we only have one more lecture of new material. So hopefully, you're on top of things, you'll be thoroughly prepared, and so on. Any questions? Yes.
So I've just noticed that that's B cross A, and then down it's A cross B. I just wanted to make sure which.
Does it make any difference?
Doesn't matter.
I'm glad you asked the question. Because it's magnitude, it does not matter. It doesn't matter because if I'm asking for a cross product, we know that reversing the order will change the sign, the opposite direction, but it won't change the length. And because these are magnitudes, again, you have a little bit of more forgiveness when they're magnitudes because the order is actually not going to change anything, which is nice. But when I did the problem, I did it as V cross A, but I could have done the entire problem as A cross V, and all of your results would have been exactly the same. The reason we usually do V cross A is actually because when you're doing it, that's the order you're finding your vectors. It just, mentally, it's easier to remember, but A cross V is going to give you the same answer. That's a good question. In that case, it just won't matter. Okay? You didn't stop. Do the roll thing.